Hi, welcome to our second lecture on Mini Excursion 3, Exponential Growth. So in the last lecture, we learned about linear growth models, and that was where you add the same amount at each transition, and remember that linear growth results in an arithmetic sequence. So today we're going to talk about an exponential growth model, and that's a model where you multiply by the same amount at each transition. And exponential growth results in a geometric sequence. So let's say we have a rabbit population that starts at 1,000 and increases by 20% per year. So I want to find out how many rabbits there are after 1, 2, 3, and n years. So I'm going to make a little table. So I've got n p sub n. And in year 0, there are 1,000 rabbits. And then to increase by 20%, I would take 20% of 1,000, or 0.2 times 1,000, and then add that to 1,000. So 20% of 1,000 is 200, so that's how much I increase by. So let's put a little note over here. I'm trying to calculate 20% of 1,000. So I do 1,000 times 0.2, and that gives me 200. And that's how much I increase by, so after 1 year, I'm going to have my original 1,000 rabbits plus 200 more. So I have 1,200 rabbits. And then I'm going to do that same process again, but this time I'm going to increase 1,200 by 20%. So a quick shortcut for how to increase something by 20% is to multiply by 1.2. So I'll explain why in just a second here. Okay, so the reason we multiply by 1.2 is because we're going to keep 100% of what we had, so that's where the 1 comes from, plus 20% more. That's where the 0.2 comes from. So I'm going to have 1,200, 100% of it, plus 20% of it. 1,200 times 1.2 equals 1,440. And if you do it the way we did the previous example, you'll also come out with 1,440. This is just a little shortcut. And then in year 3, I'm going to do 1,440 times 1.2. And I get 1,728. So if I want to write a formula for how many rabbits there are after n years, I could do it recursively or explicitly. So I'll do both of them. Now for recursively, it's pretty straightforward. What I was doing is multiplying the population of rabbits from the previous year times 1.2. So this would just be p sub n minus 1 times 1.2. And if I want to do an explicit formula, I have to look at how many times I multiplied by 1.2. So to get from one term to the next in my sequence, times 1.2 times 1.2. Times 1.2. So repeated multiplication, the symbol that we use for that is an exponent. So to get to n equals 1, I started with 1,000 and I multiplied by 1.2 one time. And to get to year 2, I started with 1,000 rabbits and I multiplied by 1.2 twice. And to get to n equals 3, I started with 1,000 rabbits and I multiplied by 1.2 1, 2, 3 times. So the pattern is that to get to any year n, I'm going to start with 1,000 rabbits and multiply by 1.2 n times, which I denote 1.2 to the nth. So those are my two possible formulas, a recursive and an explicit, for the number of rabbits after n years. That number 1.2 is called a common ratio because it's the value of the ratio of the current population to last year's population for any 2 years. So I could check this. So if I look at these two, 1,200 over 1,000 is 1.2. And 1,440 over 1,200 is 1.2. And 1,728 over 1,440 is 1.2. So that's why we call it a common ratio, but we also think of it as the multiplier, what you multiply each term by to get to the next term in the list. So here are the general formulas for exponential growth. You don't need to memorize them because we just answered a whole question about exponential growth, came up with the formulas without knowing this already. But that being said, if you like to work with formulas, these are good to have written down somewhere. So a recursive formula, you always have to give the starting amount, which in our case was 1,000 rabbits. Starting amount. And then to get from one term to the next, you multiply by the common ratio. You just take the previous term in the list times the common ratio, whatever that is. In our case, it was 1.2. And if you want to write an explicit formula, you start with the starting amount and you multiply by the common ratio n times. And the notation for multiplying by something over and over is to raise it to the nth power. Okay, so here's a different kind of setup, also exponential growth. The Earth's population was about 6 billion in the year 2000, and let's assume it takes 45 years for population to double. The population in 2045, 2090, 2450, and 2900. I want to predict those. So my list of populations, let's see, if I do n and p sub n, we'll call the year 2000 year 0. It's when we start counting, and that's 6 billion. And so 45 years later, in 2045, it's going to double. We'll be at 12 billion. And in 2090, it'll double again. We'll be at 24 billion. And I want to know what the population would be in 2450. So I could just work my way down the table till I get to 2450. So let's see, 90 plus 45 is 135. Plus 45 is 180. Continuing my table over here. 225, 270, 315, 360, 405, okay, we're getting closer, 450, there it is. So now I just have to double my populations this many times. So I have 48, 96, 192, 384, 768, 1536, 3072, 6,144 billion, right? So that's actually 6,144 billion. So this is in billions. So that's how many there are in the year 2450. I don't really want to keep writing these out to get to 2900. There's got to be some way to do it a little bit quicker. So what I'd really like to know is how many sets of 45 years have passed between the year 2000 and the year 2900. Well, 900 years have passed total, 2000 to 2900, 900 years. And the population doubles every 45 years. So I want to know how many times 45 years have gone by. So I'm going to do 900 divided by 45. And I get 20 times. That means my population, which starts at 6 billion, I'm going to double it 20 times. So I'm going to do 6 billion times 2, and I'm going to multiply it by 2, that's double it, 20 times. So instead of writing out times 2 times 2 times 2 times 2 with 22's there, I'm going to write times 2 to the 20th, because that means multiply by 2 20 times. So let's see, 6 times 2 to the 20th is 6291456. So that's 6,291,456 billion. That's a lot of people. So if I want to figure out the Earth's population in 2120, I could take a similar approach. I could say, well, 120 years have passed since 2000, 120 years. How many sets of 45 are in there? So I would do 120 divided by 45, and I get 2 2/3. So 45 goes in a full 2 times, but not quite a third time. We'll just write 2.67. So my population is going to double twice, but not quite 3 times. So it's going to be, if it doubled twice, it would be 24 million, and if it doubled 3 times, it would be 48 million. So my answer should be somewhere between 24 and 48 billion people. Answer between 24 billion and 48 billion, because we're going to double somewhere between 2 and 3 times. So let's do the same thing we did in the last problem, where I started with my 6 billion and I said, okay, I'm going to double it so many times. And the last time I doubled it 20 times because 45 went into 900 20 times. So this time I'm going to raise it to the 2.67. And let's see what I get. 6 times 2 to the 2.67, and I get 38.19 approximately billion people. So it was harder than the last example because, okay, so this was harder than the last example because when I divided the number of years by 45, I didn't get a whole number. So I couldn't double a whole number of times. But that's okay. We just follow the same procedure. We do 6 billion times 2 to the however many sets of 45 there were. And in this case, it was 2.67. And the answer makes sense because it did come out in the region that I expected it to, between 24 and 48 billion people. Okay, so let's think about a bank account as a population of dollars. Which would you rather, $1 million or a bank account that begins with 1 cent and doubles in value each day for 30 days? So, on the one hand, we have $1 million. $1 million. That seems pretty tempting, right? On the other hand, we have a penny, and we're going to double it in value each day for 30 days. So let's see what that would end us up with. We're going to start with 1 cent, and I'm going to double it, so that means times 2, 30 times, each day for 30 days. So I'm going to do times 2 to the 30th. And let's see what that comes out to. We know 1 times 2 to the 30th is 107,37418.2. 2, 4. $10,737,418.24. I want this one. More than $1 million by 10 times. Can you imagine starting with a penny and doubling in value every day for 30 days and gives you over $10 million. This is the power of exponential growth. It grows very fast. Here's another interesting exponential growth problem. It's generally difficult to measure the thickness of a single sheet of paper because it's so small, but you can figure it out using the fact that a ream of 500 sheets is 5 centimeters thick. So I'm going to do 5 centimeters divided by 500 sheets of paper, and I get 0.01. 5 centimeters divided by 500 sheets is 0.01 centimeters per one piece of paper. So I get 0.01 centimeters for one sheet of paper. So when you fold a piece of paper in half, its thickness doubles. So if you folded the paper and then fold it in half again, the thickness doubles again. So let's let T sub n represent the thickness of our paper after n folds, and I'm going to fill in this chart. So after 0 folds, the thickness of my paper is 1/100th of a centimeter. And then I fold it in half and it's going to double, and I get 2/100ths of a centimeter. Fold it in half again, so now it's folded into quarters, and the thickness would be 0.04 centimeters. Double it again and I get 0.08 centimeters. Double it again and I get 1.6 centimeters thick. Okay, so we're finally at a centimeter. That's still pretty small. Let's see if we can use this information to write an explicit and a recursive formula for T sub n. So for recursive, I would say, well, T sub n, the thickness after n folds, is equal to the previous thickness, which we denote T sub n minus 1, times 2. Just double it, because you fold it in half again. And then for explicit, we're going to start with 0.01 centimeters, and we double it over and over and over again. And in fact, we double it n times. We're going to multiply by 2 n times. So we write that as times 2 to the n. So there are our two formulas. What's the thickness after 7 folds? Well, I can use my explicit formula where the thickness after n folds is 0.01 times 2 to the n, and I'm just going to replace the n with a 7. The thickness after 7 folds is 0.01 times 2 to the 7th, which is 1.28 centimeters. Still not very big. So how many folds do you think it will take to reach a thickness of 5 centimeters? So we'll just guess and check. We'll just say, well, 0.01, we know 7 folds gets us to 1.28 centimeters. So maybe let's try 10 folds. T sub 10 would be 0.01 times 2 to the 10th. I get 10.24. That's way too big. That's way too big. We only want 5 centimeters. So maybe we'll just do times 2 to the 9th. See, after 9 folds, we get 0.01 times 2 to the 9. And I get 5.12. So that's pretty close. 5.12. So about 9 folds. to reach 5 centimeters, about the size of a ream of paper. So what's the thickness after 15 folds? T sub 15 is 0.01 times 2 to the 15th. 0.01 times 2 to the 15th is 327.68 centimeters. And centimeters is no longer a good unit for this because we have so many of them. So maybe we could convert it to meters. There are 100 centimeters in a meter. So I'm just going to divide this by 100. And I get 3.2768 meters. So 3 meters, that's like 3 yards, about a little more than, between 9 and 10 feet. 9 and 10 feet. So this is taller than a person, which is pretty big. Taller than a person. How about after 20 folds? T sub 20 would be 0.01, the thickness of a single sheet of paper, and then we're going to double it 20 times. So that is 10,485.76 centimeters. Again, centimeters are not a good unit. I could change it to meters by dividing by 100, and I get 104.8576 meters. So that's like a football field. That seems ridiculously large. So that seems ridiculously large for 20 folds. You take one piece of paper, fold it in half 20 times, and it's the size of a football field. Again, we're witnessing the power of exponential growth. When you multiply over and over, your value grows really fast. All right, let's see, 25 folds. So my thickness after 25 folds, start with your original thickness of one sheet of paper, and we're going to double it 25 times. And we get, ooh, that's a big number, 335,544.32 centimeters. Not a good unit. Let's change it to meters. We divide by a 100. So that's 3,355.4432 meters. So 3,000 meters, maybe we'll change it to kilometers. So there are 1,000 meters in a kilometer, so I can divide by 1,000. And I get 3.35, and I'm just going to stop the decimals there, kilometers. So 3 kilometers that's approximately 2 miles. Okay, so if you divide by 1.6, you get miles. So this is about 2.1 miles. Because there are 1.6 kilometers in a mile. That seems also ridiculously big. We fold a piece of paper in half 25 times, and now its thickness is 2 miles. That's nuts. So if the distance from the Earth to the Moon is 384,403 kilometers, how many times should the paper be folded to make it reach the Moon? So I want to know, what should n be? I'm going to do 0.01 times 2 to the something, and I want to get at least 384,403 kilometers. So I'm going to get to the Moon or beyond. So I know that 25 wasn't enough because that was only 2 miles, 3.35 kilometers. So maybe let's try 30. 0.01 times 2 to the 30, and n equals 30 gives me 7 0.37418.24 centimeters. Change it to kilometers by dividing by 100 and then dividing by 1,000. I get 107.37 kilometers. That is not far enough. I need to go 384,000 kilometers. So let's try n equals 40. So I'm going to do 0.01 times 2 to the 40, and I get a large number of centimeters. I'm going to change it to kilometers, and I get 109,951 approximately kilometers. So I'm getting close. If I double this to go to n equals 41, I would have 218,000, and if I double that, I would have over 400,000. So let's try n equals 42. 0.01 times 2 to the 42. Divide by 100, divide by 1,000 to get into kilometers, and I get 439,804 kilometers, which gets me past the moon. And it only took 42 folds of the paper. Not very many. And it got so thick, we passed the moon. So, again, showing the power of exponential growth and how fast it is. So, exponential growth, given that it is so powerful and so fast, is generally not sustainable. You can't keep growing that way forever. No population can keep growing that way forever, because resources like food and water and space are always finite. There aren't enough to support sustained population growth in an exponential manner. So a more realistic population growth model is called the logistic curve, which levels off at a carrying capacity of the environment. So it starts off looking exponential, but then it slows down and approaches a carrying capacity that it maintains over time. So this logistic growth might be a good topic for a project. You could look at its formula and what its graphs look like and what kind of populations grow that way. So that might be a good suggestion for something to study for your project. So that concludes the lecture on exponential growth and logistic growth. Hope you enjoyed it.